Professor Hanson, I have a question about, like, say, if we have ethane, then I sort of expect the rotation angle to be any value. Like, I sort of expect the energy spectrum to be continuous because it doesn't have to be 60, right? Is it like really something special about 0 and 60, or is it because we are just looking at?
Yeah, no, it is continuous. You're absolutely right, Wendy. It's 0 and 60 are the minimum and maximum.
Yeah.
And so, yeah, you have everything in between. And, in practice, these very simple molecules, ethane, butane, are the only ones where you get these, the numbers are actually 0 and 60. In reality, you have a lot of sort of structural constraints and things that will lock molecules and other conformers. But yeah, it's continuous, and we just talk about them because they hit the high and the lows.
Great.
Yeah.
Thank you.
Yeah.
I had a general question, so I just wanted to like kind of check two things first. When you say that a certain like substituent is in the plane, like with the line, is there another way to think of it? Like, because the way I've been kind of trying to like envision it in my head is just that like the line mean that it goes up. Like, is that an okay way to think of it? Like, if it's in plane, it just goes up in the Newman projection.
I'm just thinking before I respond. I think that's okay. Yeah. Unless it's pointing down, sort of in plane, then you'd want it going down in the Newman projection. Yeah.
Okay.
You know what I mean? But yeah, if it's in plane, I think it's safe to say if it's in plane, it's either up or down.
Okay.
In the Newman. Yeah. Yeah.
Cool. And then the other thing was when you were talking about rotating the carbons 60 degrees, so can the way we see that is by looking at substituents. So like I guess for instance, like if the H kind of like I think because one thing that I was just trying to like visualize a bit was like if it goes like if the H is originally like this way and then it like rotates all the way here, that's not 60 degrees, right? That'd be like 120. Like
that's 120. Yeah, exactly.
Okay.
So yeah, no, it's tricky. It's let me draw it because let me go to the whiteboard. Go to the virtual board here. So okay, so yeah, so if you're going, if we go like this, I'll go back to ethane. And A, B, C. Yeah, so a 60-degree rotation in the line wedge diagram basically looks like you basically exchange the sort of bond that's in plane. That bond will end up, it's not going to be the same bond, but the in-plane bond then is going down. And then where the in-plane bond was, you now have the line and the wedge. So for this rotation, I'm going to go this way. You see that? But then if you go 120, everything, all of the sort of relative orientation of the lines and the wedges ends up the same in the product, but the substituents have sort of exchanged positions. So So if I'm going a full 120, then HA is now coming out at me where HC was. HC is going back and HB is up top. Do you see that? Yeah. So it gets a little tricky, and especially this flip flop, going from this guy down to here, it looks like HA is actually moving by more than 60 degrees. And that's an artifact of, the representation. Yeah.
So in like a practice problem where we were being tested on this, would we be told what kind of rotation we'd have to do, like the angle?
Yeah, I mean, we would say rotate by 60 degrees or rotate by 120. Yeah. But just remember, it's good to think about the Newman projections because, you can see the 120s and the 60s, I think, much more clearly. And when you're looking down at these carbon atoms, you're always 120 between CH bonds, looking at it end on. And so, so 60 will always be half of that. Yeah. But we won't ask you, as long as you have the general orientation of everything correctly, we're not going to sort of, argue that looks like 45 or, you know what I mean? The other thing I didn't mention in class, I wanted to say this, but I forgot, is that these positions are arbitrary. So it is equivalent to draw this as CHA. So I can switch the positions of the lines and the wedges, that's totally fine. Cool. Any other general questions? If not, what I'll do is I thought we could go through, like bonding and ethane, for example, just because it's a little more complicated than what we covered in class and might help to identify, points of potential confusion or things that you want clarified, give you a better understanding of what these MO diagrams mean. So just feel free to interrupt me. And we're not thinking about stereochemistry, so I'm just gonna draw it flat. Okay. So so let's start with what's easy, right? So the hydrogens bring what type of orbital to the table?
1s.
Good. Yeah. So how about the carbon atoms? That's a little trick area.
Sp3.
Yeah. So the carbon atoms, Sp3 hybridized. And we said that, just to back up for a second from that, you have 4 atoms bonded to carbon, right? And we want to use equivalent orbitals for those bonds. And so we take the normal sort of ground state configuration and we excite it, is what they say. We change it so that we get half-filled orbitals in all 4 of the 2 shell n equals 2 shells. So 2p1 now, 2pz1, okay? And then what that allows me to do is then have all of these orbitals participate in bonding. And so then we're going to take these and mix them. And we get 4 of these sp3 orbitals, right? And, or I can say, can draw out the, the book's got the shapes, but, something like that.
Wait, so sorry, where did the grand state thing, the 1s2, 2s2, did that
Yeah,
come
this-
from
yeah. Thank you. Yeah. Yeah. So this idea of hybridization allows me to use all the orbitals and then they're equivalent. So you end up with 4 sp3 orbitals. And so this is kind of the first step, when you're making these MO diagrams, it's like, you got to just figure out what AOs you need to worry about, And so we've now identified the inputs, so to speak. So the H1s and the 4 sp3, okay? And then we can start to construct the diagram, okay? And so what's trickier about this example, than dihydrogen or, than dihydrogen, is that you have 2 types of bonds, right? You have the CH bonds and then CC as well. And so the diagram is going to get a lot more complicated, but we're just going to back into it very slowly here, okay? And so the first thing we're going to do is we're just going to consider the CH bonds of one of the methyl groups of one of the carbons, okay? And we're going to say, okay, let's draw an MO diagram for the CH bonds on one of those. So I need to start by putting in the orbitals on the side. So basically, we can, again, start with what's easy. Let's bring in our H1s orbitals. And I've got 3 of them. So right. Each of those is half filled. Yeah. Right, because each hydrogen brings in 1 electron. Okay. And then we have the sp3 orbitals. So we know each carbon brings 4. I'm only going to consider 1 carbon right now. Each carbon has 4 sp3 orbitals. 3 of those are going to be involved in bonding to hydrogen, right? And so I'm going to draw them over here. Okay, I'm explicitly leaving out the 4th one. We're going to pencil that in a second, but I'm just leaving that out for right now. Okay. And so we know from our electronic structure that each of those is half filled. Each of those sp3 orbitals is half filled, so I can just put 3 electrons in there. Okay. And then we allow them to mix. And remember the rule number of AOs in equals number of MOs out. So don't let the idea that we've got this hybridized orbitals and there's another carbon that we need to think about and more hydrogens, don't let that confuse you. Just focus on like what's in front of us, which is I've got 3 H1s orbitals. I've got 3 carbon sp3 orbitals. So I have 6 atomic orbitals. So whatever I'm doing right now, I better get 6 molecular orbitals out. Okay, and so 3 of those are going to be bonding, and I'll put them down here. And then 3 of them are going to be antibonding, and we'll put them up here. Okay, and then, you know, it's always nice to kind of draw the lines. Okay. And so the bonding orbitals are always adding the atomic orbitals. So this is going to be H1s. Let me draw it over here. H1s plus CsP3 by 3. Okay. And then this is going to be H1s minus CsP3 sp3 by 3. Okay. And if you want to draw out the shapes of the orbitals, you can. It's going to look something like this: HC with a sort of a change in sign again. It's not so critical. We're never going to grade you on your orbital diagram, on your orbital pictures. The only thing that's important that needs to be correct is the sort of composition of the orbital between the atoms. So do you have a bonding interaction between the atoms in the bonding orbital and an antibonding one in the antibonding orbital? And by bonding interaction, I mean, is the sign of the orbital the same as you move between the 2 nuclei? Okay, you guys follow me? So that's the bonding orbital, and then the antibonding orbital. The salient point is that the sign of the orbital changes. So, and again, the signs are completely arbitrary, but what matters is that they change as you progress down that bonding axis. Okay. So that's the hard part. And then basically you can populate, and we know that we want to fill the lowest energy orbitals first. We fill degenerate orbitals halfway before populating, pairing them up. But we have 6 electrons, so we have to fill them all. And so that describes the bonding in the CH3 groups. Okay. And then there's one other type of bond, which is going to be the CC bond, right? And so to draw the interaction diagram for that, we can put that on the same diagram. The trick is you have to know what atomic orbitals go in. So what are the orbitals that I'm worried about? Or what's the input for the CC bond?
Is it a CsP3 orbital?
Yeah, it's my last remaining CsP3 orbital, right? Because I started with 4, 3 of them are spoken for with the CH bonds, and then we've got 1 more left over. So I'm going to draw it here. I'm going to half populate it, okay? And then I'm going to jump over to the right a little more. I'm going to draw 1 more CsP3 orbital, and that's going to be from the 2nd carbon, okay? And that is also half populated. And then number in, number out. So 2 in, 2 out makes sense. So we get 1 bonding, 1 antibonding orbital. And you can pencil them in. Okay. And then populate. And so this is CC bonding. And then this one up top is, we're running out of space here. I'm going to erase what's above this stuff here. Just give it a little room. This is my CC antibonding, so. Okay. And so then if I just want to kind of, you know, put all the nomenclature descriptors in there, remember these are all sigma bonds because they're cylindrically symmetrical with respect to the bonding axis. So this is a sigma antibonding orbital. And the notation that we use for antibonding is just to put a little asterisk up there. Okay. And then the bonding is just sigma. And then it's the same thing here, sigma, sigma star. And I'll just write out antibonding, antibonding. And then these two are bonding. Okay. And so I could keep going, you know, there's 3 more orbitals here, and then I can draw the CH interactions for the second carbon, but they're identical. So I'm not going to go through that, but hopefully this helps a little bit. You can see how it gets complicated. And, you know, typically like when we draw these, you know, say we're thinking about like methanol or something, CH3OH, you know, if we want to talk about the CO bond, we don't usually draw the whole thing, like all the CH bonds and the OH bond. We usually just draw a simplified bonding diagram that has the carbon-oxygen bond, if that's what I'm interested in. So maybe I'll go and I'll just do that briefly, and then that'll be good. So, you know, so if I said to you, you know, what's the CO bond in methanol composed of, right? It would be the same sort of first step. So we'd want to identify the orbitals that are going in and then allow them to mix. So anyone want to take a stab at the atomic orbital inputs? Let me give you a little hint and say, let's start with carbon. So what's the hybridization at carbon?
Sp3.
Yeah, Sp3. So I'm going to bring in what type of orbital?
Sp3.
Not a trick question. Yeah. So I'm going to take an Sp3 orbital from carbon. So that's good. So CSP3. What's a little trickier is what's going on with oxygen, right? Because we haven't really talked much about this. Maybe you might have learned about this in prior classes, but do you know the hybridization on oxygen?
Suppose that's also Sp3.
Yeah, also Sp3. And the reason is that it's got 4 things attached to it, right? You got 2 lone pairs and then 2 bonds. So we maintain that Sp3 arrangement. So there it is. And then, you know, it's the same type of drill. So each of them is half populated, and we're going to allow them to interact. And, you know, 2 in, 2 out. So 1 bonding, 1 antibonding. So let me just. Okay. We can draw the orbitals themselves, and so they're going to look something like this. Okay. And then this is sigma star, this is sigma, and then you put the 2 electrons down there. Okay. So what you want to be able to do is, we'll never ask you, and there's no reason to. I mean, we don't do this in lab. We don't draw out the MOs for the entire molecule. It's just too complicated, and it doesn't really give you much. You don't need all that information. It's TMI effectively. What we do is we draw bonding orbitals for specific bonds, and so a realistic question is, what does the CN bond look like in methylamine, which would be pretty analogous to methanol, those types of things. So you want to be able to, basically, you want to try and become fluent in drawing MO diagrams for individual bonds, and just know in the back of your head that, in fact, everything is mixing and we've got lots of MOs, but thinking about them in terms of individual bonds is what we do 99% of the time. So that's the way to do it.
This
Sir,
is probably
how
sorry.
would we know? Sorry, how would we know that oxygen is like a relatively lower energy state
Yeah.
than carbon?
Yeah, I didn't want to get into it. We can get into it. So the great thing about these diagrams is you can extract a tremendous amount of qualitative information. And because oxygen is more electronegative than carbon, any electron is going to be happier near oxygen than carbon, okay? Because you've got more protons in the nucleus. And so that charge-charge interaction is stronger. And so what that translates to then is a lower energy atomic orbital, okay? Where this gets really cool and interesting is that there's another sort of truism of quantum mechanics that says that molecular orbitals, I'm paraphrasing here, molecular orbitals look most like the atomic orbital that's closest in energy. Okay, and so if I wanted to draw this sigma bond in a more realistic fashion, it would look something like this. That's not a great drawing. Okay, so because the input atomic orbital is lower in energy at oxygen, the resulting bonding orbital is gonna be localized more on oxygen. Okay, does that make sense? It's kind of level 2. You don't need to know this now, but you will. It'll be useful down the road, because there's another sort of rule of quantum which says that the sum of the squares of the coefficients of the molecular orbitals in a system must add up to 1 on any given atom. Okay, and so what this means is that because I've taken sort of the MO, the bonding MO, and pulled it towards oxygen, the way I'm going to reach that sort of unity value for carbon is that I'm going to polarize the antibonding orbital towards carbon, okay? And so if I draw this more realistically, it looks something like this. Okay, and so so it's fun to get into this stuff, but I don't want to overcomplicate it. But suffice it to say that we can use the relative energies of the AOs to then sort of gain insight, not just into like what the MOs are made of, but what they're shaped like in a very qualitative fashion. Okay, and this tells us that I've got a lot of this antibonding orbital behind carbon, and oxygen isn't a great leaving group, but if we replace that with something like bromine or chlorine, what we find is that we can actually bring in other atoms, which are called nucleophiles, have them attack that carbon. And this is basically the MO explanation for that, like of why that happens, is because you end up with this polarized antibonding orbital stuck behind carbon. So we'll return to this. You know, we'll revisit this in a lot of detail when we get to nucleophilic substitution, but it's good to know it now. It'll serve you well, sort of as you kind of build up your expertise here. So yeah, but you can get a tremendous amount of information from these orbital diagrams.
May I ask, like, when you look at the bonding between carbon and oxygen, why does the oxygen side has a why is that side fatter? Because I expect if the electrons are like more concentrated near there, then the boundary of 90% cloud should be narrower.
Yeah, it's so think about it. You know, in terms of like probabilities might help. So like, you know, if I'm an electron and I'm happier around oxygen, you know, there's a 70% chance I'll be there. Yeah, that's kind of what we're showing. Yeah. It's not so much that it's gotten fatter at oxygen that I've kind of stopped away from nitrogen or carbon. Yeah, yeah. So, cool. Any other questions? Hopefully that was helpful a little bit.
Professor, can you go over what bonding order kind of represents? Because I know how to, I think I remember the formula, but I don't really know, like, what does that tell us?
Bond order.
Yes.
Let me look at the book real quick. Oh, okay. So yeah, so the simple explanation of bond order is that, you know, it's kind of the number of bonds that are attached to another atom. So like the book has like, you know, CC single bond order of 1, CC double bond order of 2. It's kind of, you know, it's pretty obvious. It doesn't really tell you anything right now. It's sometimes you get to fractional bond orders, which is where it becomes a useful nomenclature. So, you know, there are, for example, I don't think we actually covered amides specifically, but this is when you have, I'm just putting up an example here. When you have nitrogen attached to a carbon with the C double bond O, this is an amide. This is the, you know, the basis of proteins are all amide building blocks. And we can draw a resonance structure where I push the electrons I can push my electrons up like that. Okay, are you with me? And so where the bond order comes in is like, you know, if you're looking at the structure on the left, so if these are, of course, same molecule, you know, they are contributors to the same structure. If we're looking at the representation on the left, you would say the CO bond order equals 2, and then the CN bond order equals 1. Does everyone agree with that? And then what is it on the right?
It would be 1 and 2.
Yeah, it'd be reversed, right? So here, based on this structure, it'd be 1 and then 2, you know? And so then, so the reality is that it's actually fractional. So it's actually, you know, CN is like 1.3 and CO is 1.7 or something in the actual structure, because it's a composite of those two. So the bond order kind of helps me to keep track of, you know, how much exact bonding there is. But to be honest, it's not a term that we, you know, refer to very frequently, but it can be useful, you know, when you're talking about resonance structures and things. Yeah. Yeah.
I have a quick question going back to the MOs on the last page. I guess 2 quick questions. One is the hybridization of the orbitals, like, is that purely dependent on how many like groups the atoms attached to? So like the lone pairs and the atoms, and if so, like, assuming that atoms are going to be abiding by like the octet rule, are we like more or less going to be dealing with sp3 for the most part for those?
So the first part of your question was accurate. So it depends on how many things are attached. And we're going to be dealing with, you know, first and second row, but sp3, you're going to start to see sp2 and sp, particularly for carbon, coming up. And so, you know, when we get to alkenes, you'll have, you know, C, and so those carbons then are sp2 hybridized. And so we'll have to learn those variants, but that'll be the extent of it.
Okay, so even though there's like, you know, 8 electrons, since some of them are like in that double bond, that would just kind of count as one group, I guess.
Yeah, exactly. You have, so there's a net 4 electrons getting shared here, because you have the sigma and the pi bond. And so you'll see, so we can account for that with the sp2 hybridization. That leaves a p orbital to form that second bond with carbon, between carbons.
Okay.
Yeah.
And sorry, really quickly, the second part was, I was just wondering if you could talk through like how to draw the orbitals that you're doing with the bonding and antibonding on the diagram, like sort of like what the little 2 circles on the outside mean, and like on top, like when you're shading, like how that all works.
Yeah. How does it work? It's kind of, so okay, so the way it works is it comes from the atomic orbital functions. And so like if I take H1s, you know, we said like that's like a nice sphere, right? Nothing, no nodes, nothing, you know, just a nice sphere. The sp3 orbitals are something like this. They're kind of these polarized dumbbells. Okay. And where that shape itself comes from is from this idea that you're adding a 2s and 3 2p orbitals. And if you like add those functions, you know, and maybe you can, I can't, you know, you can sort of, you end up with these kind of these polarized dumbbells. Okay. When I'm drawing the bonding and the antibonding orbitals, that's a similar thing. I'm taking these 2 orbitals now from the different atoms and just kind of like adding up the phases of their wave functions. And so let me see if there's an example. There might be better drawings in the book, but you end up with things that look approximately like what I drew. But let me see if I can find. Does the book not actually show a bonding orbital? It must. At any rate, I can't seem to find anything, but at any rate, the shapes come from sort of adding and subtracting the wave function. I don't know if that helps at all, but that's sort of where they're coming from. And as I said, like the key, so when you have a node in one of your sort of constituent orbitals, you're going to wind up with a change in sign at both nuclei, and that's just due to the math. When you come in with orbitals that don't have any nodes, which are basically just going to be H1s, you end up with those simpler MOs, like where you have H2 and you just kind of have like something like that, and then something like that, where this one on top is the bonding and the bottom one is the antibonding. So yeah, I don't know if that helps, but it kind of just, the general shape comes from the addition and subtraction of the atomic orbitals. And, I think it's probably safe to say that if you have a node in one of your constituent atomic orbitals, you're going to end up with sort of nodes at each carbon. So if I did like 2 Sp3s and made a bonding orbital, it would look something like that. And then an antibonding orbital would look something like that.
Yeah, okay. I think that makes sense. And so like generally when we're drawing these diagrams, like we might kind of like generally sketch that kind of next to the I guess when we're filling in the orbital, but like it's not like a super detailed thing that we would need to do.
No, exactly. It's, the main thing is that you want to, the important details are that there's a bonding interaction in the bonding orbital, i.e. no change in sign.
Mhm.
And then that there's an antibonding interaction in the antibonding orbital between the atoms. Yeah, that's really the only critical point. And then you can sort of get into that polarization that I talked about a minute ago with the CO bond and stuff. But again, it's hard to accurately draw these. I can send you guys some models, but yeah, just remember bonding, same sign across the MO between the atoms, antibonding, change in sign.
Yeah, okay, perfect. I think that makes sense.
All right.
Thank you so much.
All right, Ryan, see ya. Bye.